Hello everyone, I'm Mohsen Sombolestan from University of Southern California. I'm going to present our work on hierarchical adaptive local manipulation control for quadruped robots. Legged robots can be suitable for applications in logistic, last mile delivery, and the construction industry. Such applications mostly require navigating uneven terrain. By employing a force-based control system, such as model predictive control for locomotion, quadruped robots can traverse rough terrain while having a soft impact on the robot with a controllable friction constraint. In these applications, the robot should also be capable of manipulating heavy objects. In a practical situation, usually the robot doesn't have any information about manipulated object or the characteristic of the terrain. We aim to compensate for these model uncertainties by employing adaptive control. Therefore, by leveraging the robot's body and combining adaptive control and model predictive control, we will try to solve the locomotion and manipulation problem simultaneously. This is the block diagram of our proposed method. First, we have an adaptive controller for object manipulation. In our scenario, the object parameter, such as mass, inertia, and the friction coefficient, are unknown. So the robot tries to manipulate the object without having any information about it. And the adaptive controller tries to compensate for these uncertainties by estimating the parameters shown as theta hat and psi hat. Then we introduce our Loco-manipulation controller that considers locomotion and manipulation at the same time. To this end, we introduced a unified MPC that integrates the manipulation force from adaptive controller into the conventional MPC for locomotion controller. To elaborate on the adaptive controller, first consider the object dynamic, which also contains the friction force. Then we define the composite error S as a combination of position error and velocity error. Therefore, the reference error QR dot is defined based on the robot velocities and composite error. By these definitions, we can present the object's dynamic as a matrix of known parameter y and a vector of unknown parameters theta. This formulation can also apply to the friction force Fk as well. Finally, we introduce our adaptive control law using the estimated unknown parameters, and the adaptation law for the estimated parameter vector is designed based on the Lyapunov function, ensuring that the object follows the desired trajectory. So by computing the manipulation force, it is time to introduce our unified MPC. The robot dynamic is as follows. F is the ground reaction force for the locomotion controller, and Fr is the required manipulation force. To use the discretized dynamic in the linear MPC, we need to combine the term related to the manipulation force into the vector of a state and get the augmented state vector. Then we can introduce our MPC problem. Remember that the MPC solves for ground reaction force for each leg. So the MPC tries to regulate the manipulation force in order to not sacrifice the robot's stability. So this is the main advantages of our unified MPC. First, the adaptive control calculates the desired value for manipulation force. Then the MPC solves for manipulation and locomotion at the same time, ensuring that the robots will be stable, even if a large manipulation force is required. Okay, now let's go through some experimental results using our proposed method on a Unitary A1 robot. In order to demonstrate the effectiveness of our approach, first we compare our control system with the baseline controller. Then we'll show how the control system can adapt to object uncertainty as well as terrain uncertainty. With the conventional MPC for locomotion controller, you can see that the robot cannot walk forward when there is a 6 kilogram object in front of it, and it fails to move the object even for a couple of centimeters. However, by employing our proposed method, the robot can robustly push an unknown 6 kilogram object without having any information about the object parameters or ground friction force. We tested our controller while we increased the load gradually. In this experiment, we started with an unknown 4 kilogram object, then we add 3 1 kilogram water bottles on top of that. Then we tested the robot on different terrain. In the left, you can see that the robot pushing an object on a slope, and in the right, you can see that the robot starts from a hardwood ground with a friction coefficient of 0.2, and then it crosses a grass field with a friction coefficient of 0.8. Thank you for your attention. If you have any question, I'll be happy to discuss them during our poster session on Legged Robot on Thursday, June 1st from 3 to 4:40.